In lecture 12, we're going to continue our tour of reactions of alkenes. This is part 2 of chapter 8 in Wade. Last time we looked at 7 reactions that involve addition to alkenes. We said these reactions follow electrophilic addition is the mechanism. We looked at Markovnikov addition of bromine. We saw anti-Markovnikov addition of bromine. We saw 2 methods for Markovnikov addition of OH, as well as a parallel Markovnikov addition of OR. We looked at anti-Markovnikov addition of OH, where the OH and the H that go on across the double bond add syn, and so we get enantiomers. And we looked at anti-addition of Br2 across the double bond, where we get anti-addition of bromines across the double bond, and therefore we also get enantiomers. Today we're going to look at 10 more transformations. These are a little bit more complicated in terms of the products that they make. They're not necessarily more complicated in terms of the mechanisms, but we do get a fairly complex variety of products from these. Now think about this. Remember that in organic chemistry, our goal is often going to be to make certain products from certain starting materials. So as we learn these reactions, think about these as recipes to turn one functional group into another functional group. Some of them are very specific recipes to give very specific products. Others are more general recipes to give more general products. Just as a reminder, we've done free radical halogenation, SN2, SN1, E2, E1. We had 7 reactions additions to alkenes last time and 10 more reactions of alkenes this time. So again, don't fall behind, keep organized, keep them straight, and good luck. So let's start with formations of halohydrons. Just to go back a second, we're going to start here. The addition of Br2 and water to a double bond. We call this formation of halohydrons. And here's the big picture. We have our alkene, a double bond, and we're going to add a halogen, Br2, could be Cl2, but usually it's Br2, and water. And look at the big picture. The big picture is we get anti-addition of the bromine and an OH. By anti, again, I mean that the bromine is in one plane, in this case it's a wedge, and the OH is in the other plane, it's a dash. And as a result of that, we also get an enantiomer, because we'll see there's no way to control which group, the Br or the OH, goes in which plane. So we get anti-addition of Br and OH across the double bond. Specifically, notice that this double bond is asymmetrical. It's tri-substituted. We've got the ring carbon and an H on our top double bonded carbon, and we've got a ring carbon and another R group on our bottom double bonded carbon. So specifically, look at our product. The OH is on the more substituted carbon, and the Br is on the less substituted carbon. That means that the OH is adding to the Markovnikov position, and the Br is adding to the anti-Markovnikov position. So to understand why this is happening in this way, let's look at the mechanism. The same way that the halogen added to an alkene when we did anti-addition of the halogen across the double bond last time to make a halonium ion, the formation of halohydrons proceeds in the same way, at least for the first step. We're going to take our double bond, our alkene, that's going to add to our halogen. In this case, they're using chlorine, and we're going to make a chloronium ion. If this was bromine Br2, we'd call it a bromonium ion, and that's that 3-membered ring where we have the halogen with 2 bonds, 2 lone pairs, and therefore a positive charge. Remember that that happens by the alkene adding to one of the 2 halogens, and the halogens kind of feeding back into the original alkene to get us that 3-membered ring. Then, instead of the chloride coming back and adding from the backside of this chloronium ion and opening it up. That's what happened when we did anti-addition of the halogens. That got us our anti-dibromides, for example. But now we have water in our reaction, and water is a better nucleophile than chloride. So instead of chloride attacking the halonium ion and opening it up, water is going to attack the halonium ion and open it up. By the way, this is an error here. This should not have a negative charge in this water. So water is going to attack the more substituted carbon of this halonium ion. Remember when we looked at opening these three-membered rings, we talked about how the three-membered ring is strained and the carbon that's more substituted and can more easily deal with the positive charge is the carbon that has more electron density pulled away by the chlorine. So the water is going to be attracted to the more substituted carbon because that carbon has a larger positive charge. That will open up the ring. We now have water here with a positive charge. Our chlorine is on the other carbon, the carbon that did not get attacked. And of course, since this is an SN2 reaction, notice that the water is attacking in the same step that the leaving group is leaving. That's a SN2 mechanism. That means this relies on backside attack to open up the ring. So the water would be, say, on the bottom face, and the chlorine would be, say, on the top face. The last step is that water, or perhaps chloride, some base in solution, is going to remove that extra H from our oxygen now, and that's going to give us our OH group on the bottom and the chloride on the top. We call this a chlorohydrin, or in general, we could call it a halohydrin. This is what I was saying, that if we have this chloronium ring, the carbon with the more higher degree of substitution will have a larger positive charge because it can deal with that positive charge better. It has more electron density around it to compensate for that. So the bond to that carbon will be weaker and the bond to the other carbon will be stronger. That means that chlorine is a better leaving group from the more substituted carbon than the less substituted carbon. So that's where water is going to attack. That is by definition the Markovnikov position, the more substituted position. So the result is that we end up with the OH on the more substituted side, the Markovnikov side, the chlorine on the less substituted side, the anti-Markovnikov side, and the chlorine and the OH are always going to be anti to one another because they added in an SN2 fashion. So that is formation of halohydrins. Second reaction is nothing really new. I want to talk about hydrogenation for a moment. We talked about hydrogenation before. This is the addition of H2 across a double bond. Usually it's done via a catalyst with platinum, palladium, or nickel, some kind of heavy transition metal as our catalyst. And H2 adds across the double bond. We use 2 electrons from the H2 for one bond and 2 electrons from the pi bond for the other bond. One thing we didn't look at before is the mechanism, and it's kind of a cool mechanism. What the catalyst does is it essentially adsorbs the H2 onto the metal. So the platinum or palladium or nickel, little chunks of metal that we're going to use in our solution, cause the hydrogen molecules to split. And the hydrogen molecules end up getting kind of stuck all around the metal, the face of the metal. Then what happens is when our alkene comes in contact with the metal, it's going to brush one face of the alkene along the surface of the metal like we see here, and it's going to pick up those 2 hydrogens. But that means that the 2 hydrogens are always going to be adding from the same face of that double bond. They go in at the same step. They go on the same step. And as a result, they're going to be added from the same face. We call that syn addition. We've seen syn addition before. Think about the alkene as being flat, because it is. It's sp2 hybridized, planar. If we do H2 and platinum as our reactant, we know that the H's are going to add syn from the same side. Here we're adding them to the bottom face. So the H's are going to be down, and that's going to force the deuteriums in this case to be up. That causes interesting stereochemical outcomes. If this was not a symmetrical molecule, this is a symmetrical molecule, as you can see. So this is actually a meso compound. But if one of these deuteriums was a methyl instead, then we would have a stereocenter here with a certain configuration, and a stereocenter here, a different stereocenter. Imagine the deuterium being a methyl with a different configuration, and we would have chiral compounds, and therefore we could have enantiomers. We would not get the diastereomers, though, because the H's are always going to add syn. They're never going to add anti. Reaction 3, we're moving right along, is addition of carbenes. This molecule here in green is called a carbene. This is a very interesting species of carbon. It's a neutral carbon. Look at the formal charge. It's got 2 bonds and 2 lone electrons. So its formal charge is 0. It's neutral, but it's highly reactive because it does not have an octet. It's only got 6 electrons around it. We call this methylene specifically. It's a single carbon carbene, so we call it methylene. A methylene is both nucleophilic and electrophilic. It's nucleophilic because it has a lone pair of electrons that it can donate. It is electrophilic because it is missing its octet. It is happy and willing to accept a pair of electrons to give itself an octet. So what methylene will do to an alkene is it will get attacked by the alkene while simultaneously attacking the alkene. So we have this cyclic reaction going on where we're making one bond to the methylene carbon from the alkene, and we're making another bond from the methylene to the alkene. And what we end up with is a 3-membered ring, a cyclopropane ring. Now, this is a very strained product. A 3-membered ring is very strained. These are 60-degree bond angles on sp3 hybridized carbons, which want to have 109.5-degree bond angles. So why do we form an unstable product? Well, the reason we can form an unstable product is because the methylene reactant is even more unstable. The product is relatively low energy relative to the carbene. So we're going to start with very reactive reagents, and we're going to be able to make a 3-membered ring, even though it's not that stable. It is stable compared to methylene. So methylene is so unstable that you can't really bottle it. You can't just go find a bottle of methylene sitting on the shelf. It doesn't exist. So the way we have to get methylene is by an in situ process. Basically, we have to make the methylene at the same time that we are doing the reaction. So there's a more stable molecule, something at least relatively more stable than methylene, called diazomethane. It looks like this. It's an N double bond CH2. There are 2 resonance structures to diazomethane. The middle nitrogen always has a positive charge, but the negative charge can basically be spread out from the nitrogen on the left to the carbon on the right. Notice, though, that in the right resonance structure, we have N2, N triple bond N. That is a very, very, very stable leaving group. N2, nitrogen gas, is a wonderful leaving group because N2 is very stable, and as a gas, it bubbles away. So all that it takes is a little bit of heat or ultraviolet light to cleave that bond. That N plus CH2 minus bond is very weak, and it can absorb a little bit of ultraviolet light or thermal energy, and that bond will break. N2 will leave, it'll fall off and bubble away, and we'll be left with methylene. So we can make a cyclopropane ring from an alkene by using diazomethane. Now, one problem with diazomethane, like I said, it's very reactive. It happens to be less reactive than methylene, but it's still very reactive. And it's a very nasty reagent. It's in fact cancerous, cancer causing. So you generally don't want to use diazomethane in large quantities. It's great for using, say, microscale reactions when you're only trying to make a couple milligrams of product. But if you're going to do an industrial process where you're trying to make kilograms or tons of your product, diazomethane is not something you'd want to use. There's a better way to do the same thing, a better way to generate methylene and therefore create a three-membered ring from an alkene, and that is called the Simmons-Smith reaction. Again, notice that we start with an alkene and our product is a three-membered ring, a cyclopropane. But instead of using diazomethane, we use what's called the Simmons-Smith reagent. This is ICH2 ZNI. This is what we call a carbenoid. It is carbene-like. The way we make the Simmons-Smith reagent is we take diiodomethane, CH2I2, and a zinc-copper amalgam, and these two reactants react to make the Simmons-Smith reagent that essentially gives us a CH2 methylene. We say methylene is formed in situ. So all we have to do is take our alkene, react it with CH2I2 and a zinc copper amalgam. You can even make the zinc copper amalgam in the same process by starting with zinc metal and copper chloride. These guys will make the Simmons-Smith reagent that will generate a carbene in situ, and we will get our three-membered ring. This is a relatively low yield process because the methylene is so reactive. There are lots of other byproducts that could potentially form. So 59% is relatively low for these types of reactants, but it's the best we can do. There's a parallel version of the carbene addition that not only generates the three-membered ring from our double bond, but it generates a three-membered ring with two bromines on it. We start with bromoform, CHBr3, that's bromoform, and we use basically a strong base in aqueous solution. So in this case, they're showing KOH in water. And what happens is that hydrogen on bromoform is fairly acidic. It can be removed by the hydroxide to make CBr3 minus. Now, you might be thinking, why would this hydrogen be acidic? If you remove this hydrogen, you get a carbon minus. And we've talked about already how carbon minus is not good. Carbon is not electronegative. It does not like to make negative charges. That's why normally hydrogens on carbon are not acidic. But this is CBr3 minus. It's a carbon minus with three very electronegative bromines on it. Having three electronegative bromines on a negatively charged carbon means that that negatively charged carbon has a lot of its electron density being pulled away from it and is being stabilized by these three bromines. So the CH hydrogen in bromoform is easily removed to make CBr3 minus. That CBr3 minus then will rapidly decompose. One of those bromines will leave as a bromide, and that will leave us with a dibromocarbene. Instead of having the two H's and have CH2 methylene, we have dibromocarbene, and we end up with the Br2 on this. Now, this is a geminal Br2. We've talked about vicinal dibromides. This is a geminal dibromide. This is just an example of a way we can make geminal dibromides. It's also an interesting reaction from the sense that it shows why CH in CHBr3 is an acidic hydrogen. This is an interesting concept that a carbon minus can be stabilized and can be readily formed as long as it is surrounded by enough electronegative groups. Carbene addition, making this three-membered ring, is interesting because the products will often have stereochemistry to them. Here's a disubstituted double bond. Remember, these are phenyl groups. We talked about that before. And here we have a trans double bond or an E double bond. And when we make the three-membered ring, notice that these carbons become stereocenters. Here's our two carbons that were involved in the double bond here. Here's the third carbon that we added in our three-membered ring. In this case, we used chloroform, so we have the geminal dichlorides on there. But these two carbons that were involved with the double bond are now chiral. They've got the phenyl group, the hydrogen, the ring carbon with the phenyl group, and the ring carbon with the two chlorines. So the other asymmetric carbon has the same four groups: phenyl, hydrogen, ring carbon with two chlorines, and ring carbon with a phenyl. Notice that the arrangement of the phenyl groups relative to one another is that they are trans or they are anti. The stereochemistry of the reactant, a trans double bond, is retained in the product. Those phenyl groups remain trans to one another. One of them would say be a wedge, the other one would be a dash. If we have a syn alkene to start, or a cis alkene to start, a Z alkene, and we do a carbene addition, in this case they're using bromoform, these ethyl groups, which were cis to one another in our reactant, remain syn to one another in the product. They will both be down or both be up, both wedges or both dashes. Why does it happen that way? Well, because the addition of the carbene happens in one step. This is a concerted addition, and so there's no opportunity for the groups on the alkene to reconfigure themselves. If we added the carbon to one carbon first, and then we added it to the other carbon second, in that intermediate step, there would be the opportunity for this, what is now a single bond, to rotate, and we would get a mixture. But because this addition is happening at the same time, we are adding one carbon in while the other carbon is giving its electrons away, these carbons never have time to rotate. That pi bond never has a chance to rotate after it breaks. So whatever configuration the original groups are in, they're also in that same configuration in the product. That will be a trend that you will see in a lot of reactions. In fact, if you go back and look at some of our reactions from the other day, remember that we added the BH2 and the H in this hydroboration oxidation reaction. We added them at the same time, in the same step, in one concerted step, and as a result, the H and the OH added syn. Here, when the bromines added, they added in two steps. First, we added one bromine in the bromonium, then we added the other bromide as the nucleophile. When we had two steps, they were anti. When we had one step, they were syn. We are also seeing that here. When we add the Br and the OH to make a halohydrin, we're doing it in two steps. First, we add the halogen to make the chloronium or the halonium. Then we add the water, which becomes the OH. Two steps, and they are anti. One is wedged, one is dashed. When we did hydrogenation, we added them in one step. The two hydrogens go on at the same time. They go on the same face, therefore they are syn. Here, when we add the carbene, the two bonds that we are forming to make this three-membered ring are being formed in one step. Therefore, we don't get that rearrangement, and whatever configurations our groups are in to begin with are the groups that they are at the end of the reaction. Our fourth reaction, along the same veins as carbene formation, is epoxidation or epoxide formation. An epoxide, also called an oxirane, is a three-membered ring where one of the atoms is an oxygen. Before, we were just making with carbenes three-membered rings of carbons. Here we have three-membered rings with an oxygen. That's an epoxide, and epoxides are formed by starting with an alkene and adding what's called a peroxy acid. You'll notice that this is like a carboxylic acid, except that there's an extra oxygen between the C and the H. This O-O bond is called a peroxide bond. So we call this a peroxy acid. That peroxide bond we've mentioned before is very reactive. It's very unstable. You can really use any type of peroxy acid. There's not a specific type of peroxy acid that's necessarily has to be used. You'll notice that this is a general peroxy acid. They're just using an R group. So a carboxylic acid, like acetic acid, could have a peroxy acid cousin. So this would be peroxyacetic acid, just like acetic acid with an extra oxygen. Here's benzoic acid. Here's peroxybenzoic acid, just like benzoic acid, but it's got an extra oxygen in it. So this is an interesting mechanism. We're also making a three-membered ring, like we said, like with carbenes. So let's see if it works the same way. It kind of does. Here's the mechanism. The mechanism begins by the double bond, again, acting as a nucleophile, as it does in all these cases. It's going to add to that extra oxygen, the oxygen that makes the peroxy acid different from a normal carboxylic acid. But instead of that oxygen feeding directly back into the double bond like the carbene did, there's this other cyclic pathway that occurs. The electrons in that peroxide bond swing across and make a double bond between the other oxygen and the carbon. That causes carbon to lose a bond, and it's going to lose the bond to its other double bonded O. That pi bond is going to act kind of as a leaving group, but it's not really going to leave. It's going to take off and grab that hydrogen on the end. It's an acidic hydrogen, so it can be grabbed by two electrons. And that's going to liberate this last pair of electrons, and they feed back into the remaining carbon in our double bond. This happens in one step. There's 4 errors here. 1, 2, 3, 4. And we get, since it's happening in one step, all the bonds are being broken and formed simultaneously. We get this cool looking transition state. Therefore, we get our epoxide, and what's left is a regular acid. Notice that this oxygen, the extra oxygen that got attacked in the first step, is the one that gets onto the double bond, and the other oxygen ends up being the double bonded O, and the double bonded O ends up being a single bonded O with an H on it. So that gives us a regular carboxylic acid. Let's think about stereochemistry. This is happening in one step, just like carbene addition happened in one step. So we should be able to conclude then that the geometry of the double bond is preserved in the epoxide. That is actually the case. Here we see that if we start with a cis double bond and we do an epoxidation, those two groups remain cis to one another, or syn, you might say. If we start with trans groups, so this is an E double bond instead of a Z, our groups will be trans. They will be anti to one another. Again, we're making stereocenters. These carbons that were involved in the double bond are now involved in this three-membered ring, and they have now 4 groups on them. The H, in this case the methyl, the O in the ring, and the other carbon in the ring. That's 4 dissimilar groups. So 2 stereocenters are formed, and they are formed simultaneously. Basically, this O being added in one step is always going to be added to one face of that alkene, and that is added in that same step. So these groups are always locked in that same position. The prototypical epoxidation agent is called MCPBA. That stands for meta-chloroperoxybenzoic acid. You look at this, you see this is peroxybenzoic acid from our previous slide, but it's got a chlorine on the ring. And specifically, we'll learn this later, but this is called the meta position on this ring. So this is a peroxybenzoic acid with a meta-chloro. So MCPBA is almost always the epoxidizing agent that's used. You could use, like I said, any peroxy acid would be acceptable. All right, reaction 5. We're going to now do something with these epoxides. Epoxides, again, being a strained ring, are fairly reactive, but they are even more reactive than a normal cyclopropane ring that we form from carbenes, because the O in the epoxide ring is a good leaving group. So there are two ways that you can open an epoxide. Both ways will give you anti or trans vicinal diols, dialcohols. But it turns out that doing it under acidic conditions or basic conditions lead to very different products. In this case, in reaction 5 here, we're looking at the acid catalyzed ring opening of epoxides. So here's an epoxide, and now I'm giving us very specific stereochemistry so I can illustrate this. We're starting with an epoxide with the ring oxygen down and some R group up on this carbon, and therefore we'd have some H group, hydrogen, up on this carbon. Look what happens when we open up the ring. We end up with trans vicinal diols. Vicinal diols because they are on neighboring carbons, dialcohols, diol, and they are trans. One is up, wedged, one is down, dashed. Look what's going on here with the stereochemistry, though. Notice that the stereochemistry on the more substituted carbon, the carbon with the R instead of the carbon with the H, is getting inverted. Here the R was a wedge and the O is a dash. And in the product, the R is a dash and the O is a wedge. If that carbon is getting inverted, it's a good clue that it's undergoing an SN2 type reaction. That is indeed the case. Here's the mechanism. The first step is going to involve protonation of the oxygen in the epoxide ring with our acid. So our O will use its lone pair to grab an H plus from our acid. That will give us a protonated oxygen, which is now a very good leaving group. Water then will add to the more substituted carbon of that ring and open it up. This is exactly the same as opening up the halohydrin ring, the chloronium or bromonium ring in the halohydrin formation. Water is adding to the more substituted side of this three-membered ring and opening it up as a leaving group. Again, this is SN2, addition and substitution and the leaving group leaving in one step. So this has to occur from the back side. That means that the OH adds to one face and the OH leaves from the other face. Then we have one last step, our water that added. That O now has an extra hydrogen on it, an extra bond, and it can lose that hydrogen to water to regenerate our acid. So we have two OHs on neighboring carbons. They are anti because we opened the ring from the back side. And the OH that went on to the ring, the OH that attacked the ring, we can say, added to the more substituted carbon. That's why here, the more substituted carbon gets inverted. Since this epoxide ring is down, the back side of that ring is the top face of this molecule. So imagine our OH attacking this more substituted carbon from the top face and kicking the ring off from the bottom face. When it attacks from the top face, it attaches from the top face. So our OH becomes wedged. Our R gets kicked down to be a dash. But the other OH did not get inverted. This O on this other carbon did not get inverted, so it stays as a dash. Let's look at what happens under basic conditions. Here I'm starting with the same starting material, the exact same thing, but instead of using acid and water, I'm going to use base and water. Look at our product. It's different. Compare our product here under basic conditions to our product here in acidic conditions. What's different? The difference is the stereochemistry. Here's basic conditions. In this case, under basic conditions, which carbon got inverted? It was the less substituted carbon that got inverted. Our more substituted carbon maintained its stereochemistry. The O was dashed, the R was wedged. The O remains dashed, the R remains wedged. On the less substituted carbon, the O was a dash, now it's a wedge, which means that it's that carbon that got attacked. So the difference between acid catalyzed opening of epoxides and base catalyzed opening of epoxides is the carbon to which the nucleophile will add. Under acidic conditions, we're adding the water to the more substituted carbon and opening the ring. Under basic conditions, we're adding hydroxide to the less substituted side of the ring and opening the ring. That way we get inversion on the less substituted carbon. The O minus now is the leaving group. That's a little bit different. In this case, we can have O minus being a leaving group because we are in basic conditions. We have NaOH floating around, so O minus is nothing new here. So that's why we can ring open this and make an O minus and not have to protonate it with acid. If we have an acid, this has to be protonated first. So after the hydroxide attacks, we open up the ring from the back side. We have O minus here. That will then get reprotonated from our water to remake our base, and we get to our product. So under basic conditions, hydroxide attacks the less substituted carbon. Do not confuse these two. Keep these straight. You will see over and over and over that when the three-membered ring is protonated, or when the three-membered ring is positively charged, attack occurs from the more substituted side. That was the case for the helonium ion. We attacked from the more substituted side. When it is not protonated, or when it is not positively charged, we add to the less substituted side. Acidic versus basic. Here's your summary slide. This is what we just saw. Starting from the same starting material, you can control which enantiomer of the product you get based on whether you use acidic conditions or basic conditions. Another way to look at it is this way. Here we're starting with one enantiomer of our epoxide with the epoxide ring up and the methyl down. We'll call that A. Here we're starting with its enantiomer with the epoxide ring down and the methyl up. So A and D are enantiomers. A, under acidic conditions, will get attacked from the bottom face. Since the ring is up, it'll attack from the bottom face of the more substituted carbon. So we will be inverting at the methyl carbon, the carbon bearing the methyl group. So that's what we see here. The carbon bearing the methyl group gets inverted. If we have basic conditions, we're going to be adding to the less substituted face. So the carbon without the methyl group is going to get inverted. We're going to add our hydroxide from the bottom face of the less substituted carbon, and we're going to get C. B and C are enantiomers, like we just saw. We can control which enantiomer of the product we get based on which reagents we use. But if we start from the other enantiomer, if we start from D, the enantiomer of A, we will get to B by basic conditions instead of acidic conditions. And we will get to C from acidic conditions instead of basic conditions. Again, we're going to be adding from the top face of D to open up the ring, and basic conditions will attack the less substituted side. So we're going to invert at the less substituted carbon to get to B. And we need to invert at the more substituted carbon to get to C. Okay, so we saw two ways now to make antidiols. We can make antidiols by opening up an epoxide under acidic conditions, or by opening up an epoxide under basic conditions. And we know that we can make that epoxide from an alkene by using MCPBA, for example. So 2 ways to make antidiols from a double bond. First, epoxidize it, then open it up under acidic conditions or basic conditions. So wouldn't it be nice if we had some way to do syn addition from an alkene to get syn diols instead of antidiols? Indeed, there is a way. There's always a way, isn't there? The way we do it is with osmium tetroxide and hydrogen peroxide. This is osmium tetroxide, OSO4. And what we get is, again, syn addition of alcohols across our double bond. This is kind of what the mechanism looks like. 2 of the 4 oxygens in osmium tetroxide add to the double bond, and they add to the double bond in one concerted step. So imagine the double bond coming out and attacking one of the oxygens. The oxygen loses one of its bonds to become a lone pair on osmium, and then the other oxygen gives its pi electrons back to the carbon that lost the pi electrons in the first place. That gets us this 5-membered ring, this complex here, and hydrogen peroxide will then oxidize that off. It'll break this OSO bond and give us alcohols on our ring, but will also donate 2 oxygens back to the osmium to regenerate our osmium tetroxide. In that sense, OSO4 is a catalyst. The O's are ultimately coming from the hydrogen peroxide, which will get consumed. Now, because again, this is happening in one concerted step, the 2 O's go on at the same time, and therefore they must go on from the same face. The osmium, for example, will approach from the bottom of the alkene or from the top of the alkene. So the O's will either both be on the top or both be on the bottom. So again, one concerted step, you get syn addition. 2 separate steps, you get anti-addition. Now I want to note, osmium tetroxide is brutally toxic. It's fatal at very, 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 very low levels. So it's really fine. It's fine to use it on paper if we're going to do it in class, but in lab, you would normally do everything you can to avoid using OSO4 because it's a terrible reagent to work with. Another reagent that will do this exact same reaction, it will get you the exact same product, is called potassium permanganate, KMnO4, and you need basic conditions to do this. A little bit different mechanism. Instead of having the extra oxygens come from the hydrogen peroxide, they come from hydroxide. But KMnO4, the MnO4, looks a lot like the OSO4. And so it kind of works the same way, but it's way, way, way less toxic. One slight annoyance, though, is that KMnO4 is what I call a promiscuous reagent. KMnO4 will react with everything it can find, and depending on what it reacts with, it will make a plethora, a constellation of products. So we will see KMnO4 be used a lot. We will see KMnO4 being used hot and cold, under neutral conditions or basic conditions, with alkenes, with alkynes, with alcohols, with ketones, with carboxylic acids. We'll see it be used in all kinds of contexts. So this is your first introduction to KMnO4. If you have a hard time keeping straight what conditions you need to use KMnO4 in, just use OSO4 for the dihydroxylation of the alkenes. Again, using it on paper is fine. I don't care. Okay, we're going to switch gears a little bit. We're still going to be doing reactions on alkenes, but we're going to kind of move away from the electrophilic addition type of reactions. And we're going to look at a few reactions that are called oxidative cleavage reactions. These are oxidative cleavages of alkenes. Now, in general chemistry, you learn about oxidation and reduction. About oxidation is losing electrons. Leo says Ger, right? Lose electrons is oxidized. Gain electrons is reduced. Leoger. Lose electrons oxidized. Gain electrons reduced. Leo says Ger. Or oil rig. Oxidation involves loss of electrons. Reduction involves gain of electrons. OIL. Oxidation involves loss. RIG. Reduction involves gain. That's true. There's nothing wrong with using that. But in organic chemistry, it's a little bit easier, rather than trying to keep track of electrons, to keep track of just what atoms are being bonded. So in organic chemistry, anything that increases the number of carbon-oxygen bonds and or decreases the number of carbon-hydrogen bonds, we're going to call oxidation. We are increasing the oxidation, the number of oxygen bonds present. Reduction is the opposite. Reduction will be anything that decreases the number of CO bonds and or increases the number of CH bonds. Sometimes these things happen simultaneously, meaning we increase the number of CO bonds while we decrease the number of CH bonds. So both of those things are involved in oxidation. Sometimes it might be one and not the other. Sometimes you might decrease the number of CH bonds without increasing the number of CO bonds. But either way, increased number of CO bonds and or decreased number of CH bonds is oxidation. Decreasing CO bonds and or increasing CH bonds is reduction. So here's the general picture for oxidative cleavage. We're going to take our double bond, and with some oxidizing agents, we're just going to cleave the double bond right in half. It's like taking an axe and hacking a piece of wood right in two. And in place of that carbon-carbon double bond that gets broken, each carbon is going to gain a double bond O. So we're breaking a single molecule into two, and we're kind of patching the hole on both pieces with a double bond O. So in this respect, each carbon is gaining 2 bonds to O. So each carbon is getting oxidized, and we are cleaving the double bond. So it's oxidative cleavage. Now I'm going to show you that different oxidizing agents give different products depending on the substitution of the alkene. Here's what I mean by that. Here's our old friend KMNO4, already our old friend. So before, like I said, here we use KMNO4 to make syn addition of alcohols. This is KMNO4 basic. In oxidative cleavage, we're going to take a double bond, add KMNO4, but instead of using basic conditions, we're going to use hot conditions, hot, warm, and concentrated. The first step is going to be the same. We're going to get that syn addition of those diols. But the reaction is not going to stop there. In brackets means that this is an intermediate. This is formed, but it's not isolated. Before the glycol, this diol, can be formed, that carbon-carbon bond is split. And it is split, like we saw, and when it is patched, it gets patched with that double bond O. So the carbon on the left with the 2 R groups gets a double bond O with the 2 R groups, and the carbon on the right with the H and the R prime gets an H and an R prime. Now, the ketone can no longer be oxidized. We cannot increase the number of oxygen bonds or decrease the number of hydrogen bonds. We're stuck here. The ketone is stable at this point. But the aldehyde, notice that in this case, carbon had a hydrogen on it. And so the aldehyde can be oxidized. That carbon-hydrogen bond can become a carbon-oxygen bond. So we will get 2 products from this. We're going to cleave the double bond in half. The side with the 2 R groups becomes a ketone. The side with the H on it will start as an aldehyde, but will get further oxidized to the carboxylic acid. That H will get converted into an OH. Here's what here's kind of the logic. We're starting with a tri-substituted alkene. Our first oxidation product, the COH bonds can still get oxidized. We can turn a single bond CO into a double bond CO. So we're going to do that, and in order to do that, we have to cleave the carbon-carbon bond. We get a ketone that cannot get oxidized and an aldehyde that can get oxidized to a carboxylic acid. To summarize that, if we were to have a tetra-substituted alkene with all R groups, we're going to cleave that double bond, replace it with double bond O's, and we have all of our R groups that are resistant to oxidation. If we have a tri-substituted double bond, we're going to cleave that. We're going to have the two R groups become part of a ketone, but the H would become part of an aldehyde, which would get oxidized to the carboxylic acid. If we have two H's in this cis double bond, that's going to get cleaved. We're going to place the double bond C with double bond O's, and the H's are going to get oxidized to oxygens to make carboxylic acids. Notice, this is probably obvious, but the geometry of the alkene in the starting material is indetectable in the product. This could have been a cis double bond like I drew here, or I could have made it a trans double bond. You would not be able to tell in the product. The identity of the stereochemistry of the double bond is lost as soon as it is cleaved. One last reaction, if we don't want the carboxylic acids, but instead want the aldehydes, that, remember in our previous slide here, the aldehydes were oxidizable by KMnO4. It was not isolated and would get converted into the carboxylic acid immediately. If we want to retain the aldehydes, we're going to use something called ozonolysis. And there's a mistake in this slide. I want to correct that. This reaction, ozonolysis, basically means breaking lysis by ozone, which is O3. So ozonolysis is simply a more mild oxidizing agent than KMnO4 is. I put mild in quotation marks because it is not a mild oxidizing agent. Ozonolysis, ozone, is a very, very, very nasty oxidizing agent. But as far as these functional groups go, ozonolysis does not oxidize the aldehyde the same way that KMnO4 does. So in that sense, you can think of it as being mild because it is not able to oxidize the same things that KMnO4 can. So the error in this slide is that this is not a one-step reaction. You do not use O3 and DMS together. You use these in separate steps. So this should say 1 O3 and then 2 DMS. 2 steps. First ozonolysis, then DMS. DMS is dimethyl sulfide. It's this, CH3SCH3. It is responsible for converting an intermediate that is formed by O3 into these products. And the way that it does that retains the hydrogen instead of converting it into an oxygen. I can show you more about how ozonolysis works during our workshop if you're interested. It's a really cool reaction, but it's not something that you need to know in this class. So here's a summary of our reactions. What did we do today? We did halohydrogen formation. We made the bromonium ion, then opened it up from the backside with water to give Markovnikov OH and anti-Markovnikov bromine. 2 steps, the groups go anti. We did hydrogenation like we saw before, but we learned that the 2 H's go on simultaneously and therefore they are syn to one another. We looked at carbene addition to make 3-membered rings, either with 2 H's or with 2 bromines, doing the Simmons-Smith reagent or the modified Simmons-Smith reagent, the bromoform addition. And again, because the addition of the carbene occurs in one step, the groups retain their stereochemistry. If they start as cis in the double bond, they remain syn in the product. If they start as trans in the double bond, they remain trans in the product. We looked at addition of an epoxide to a double bond using MCPBA, metachloroperoxybenzoic acid. Then we looked at ring opening those epoxides. Since forming the epoxide occurs in one step, again, just like addition of the carbenes, our groups retain their stereochemistry. We can ring open that epoxide under acidic conditions, adding to the more substituted side, or we can ring open it in basic conditions, adding to the less substituted side, but always from the back side of the ring. We are always opening the ring from the back side in an SN2 type fashion. That gets us anti-vicinal diols. Again, since we are adding the two O's in separate steps, first in the epoxide and then from the water or hydroxide, they're going to be anti, not syn. But to get syn diols, we can add the OHs in one step using OSO4 and H2O2, osmium tetroxide. Alternately, you could have used KMNO4 basic to make the syn diols. Then we saw that we could cleave the double bond and have carboxylic acids and ketones using KMNO4 hot, or we could cleave the double bond and get aldehydes and ketones using ozonolysis, which is a two-step reaction, first involving ozone and then involving dimethyl sulfide. Okay, make flashcards, learn these reactions, memorize the trends and the patterns, learn the big picture, and learn the mechanism. This is the end of lecture 12. Our workshop from today's lecture is Stromanus chapter 9 and 10.